Hello everyone, welcome to our presentation. Today I am going to explain our project titled AI powered smart farming robot for insect detection, target spraying and IoT based environmental monitoring. This project comes under the domain of robotics and artificial intelligence. The main objective of our project is to automate pest detection and pesticide spraying using AI while also monitoring environmental conditions using IoT. Our team members are Mahesh Manikam, Jai Balaji and Harsh Bothra. This project was developed under the guidance of our internal mentor. Now let's begin by understanding the problem in the current agriculture system. In traditional agriculture, most farming activities are still done manually. One of the biggest problems is pest detection. Farmers have to physically inspect crops across large areas. This process is not only time consuming but also inconsistent because human observation can miss early stage infections. Another major issue is pesticide spraying. Currently, pesticides are sprayed across the entire field without identifying the exact infected areas. This leads to wastage of chemicals, increased cost, harm to healthy crops, environmental pollution. Also, there is no proper system to monitor environmental conditions like temperature and humidity in real time. These factors are very important because pest growth depends heavily on environmental conditions. So, our project aims to solve these problems by introducing an intelligent, automated, and efficient system. Our proposed system is an AI-powered smart farming robot. It is capable of monitoring crops, detecting harmful insects, and spraying pesticides only where needed. We use a deep learning model to detect pests from images captured in real time. Along with this, IoT sensors are used to measure environmental conditions such as temperature and humidity. This data is sent to the cloud or mobile application, allowing farmers to monitor their fields remotely. The robot moves autonomously across the field, reducing manual effort. Overall, the system improves efficiency, reduces chemical usage, and supports sustainable agriculture practices. Before developing our system, we studied several research papers related to precision agriculture. The first paper focuses on advancement in precision spraying technologies. It explains how robots can spray pesticides accurately using sensors and intelligent systems. The second paper discusses route optimization using algorithms like the traveling salesman problem. This helps robot cover the field efficiently with minimum time and energy. From these studies, we understand importance of automation, need for precision spraying, efficient robot navigation. These insights helped us design our system more efficiently. There are several challenges in the existing agriculture system. First is high labor dependency. Farmers have to manually monitor crops and spray pesticides, which is inefficient for large scale farming. Second is excessive pesticide usage. Since spraying is not targeted, chemicals are wasted and may damage crops and soil. Third is limited coverage and accuracy. Fixed systems cannot monitor the entire field, leading to missed pest detection. Our system addresses all these challenges by using AI, robotics, and IoT technologies. This slide represents the complete architecture of our AI-powered smart farming robot. Let me explain the workflow step by step for better understanding. First, the system starts with data collection. We use sensors like temperature and humidity sensor along with a camera module to collect real-time data from the field. Next, the captured images are sent to the AI model, which is trained using YOLO V11. This model processes the images and identifies whether any harmful insects are present. At the same time, environmental data is processed to understand conditions that support pest growth. The communication between components is handled using the ESP8266 Wi-Fi module, which sends data to the cloud and receives response. The Arduino Uno acts as a central controller, coordinating all operations such as movement control, sensor data processing, decision execution. If pests are detected, the system triggers the spraying mechanism automatically. So overall, this architecture ensures a continuous cycle of sensing, processing, decision, and action. This makes the system fully automated and intelligent. Now let's look at the core hardware components used in our system. First, the power supply unit is responsible for providing a stable voltage to all components. It converts AC to DC and regulates it to around 5 volt, ensuring safe operation. Next is the Arduino Uno, which is the heart of the system. It acts as the main controller and controls all connected devices. It processes sensor inputs and sends signal to motors and actuators. Then we have the Node MCU based on ESP8266, which provides Wi-Fi connectivity. This enables real-time communication between the robot and cloud or mobile applications. Finally, the LCD display is used to show real-time information such as temperature, humidity, pest detection status, robot activity. This helps us monitor the system without external devices. In addition to the core components, we use several hardware modules for the movement and control. The L293D motor driver IC is used to control the direction of DC motors. It allows the robot to move forward, backward, left and right. The ultrasonic sensor is used for obstacle detection. It sends ultrasonic waves and measures the distance to nearby objects. This helps the robot avoid collision and navigate safely. The relay module acts as a switch. It is used to control high-powered devices like the pesticide sprayer. The DC motors convert electrical energy into mechanical movement. These motors enable the robot to move across the field effectively. Together, these components ensure smooth navigation and accurate operation. Now let's move on to the software side of the system. We use embedded C programming to write code for the microcontroller. This allows us to control sensors, motors and other components effectively. The Arduino IDE is used to write, compile and upload the code. It provides a simple interface and supports debugging through error messages. For AI processing, we use Python-based frameworks to train and run the YOLO model. So overall, the software ensures proper coordination between hardware and AI modules. Our system is divided into multiple functional modules. The first module is AI model training using YOLO V11. In this module, we collect crop images, annotate insects manually, train the model to recognize pests. The model learns patterns such as shape, size, and texture of insects. Once trained, it can detect pests in real time with high accuracy. The second module is autonomous navigation. The robot uses ultrasonic sensors to detect obstacles in its path. Based on sensor input, the robot automatically changes direction. We also use environmental sensors like DHT11 to monitor temperature and humidity. This helps in understanding conditions where pests are more likely to grow. The third module is IoT based monitoring and control. In this module, all sensor data and detection results are transmitted using the ESP8266 module. Farmers can monitor this data remotely through cloud platforms or mobile applications. The system can also make decisions automatically without human intervention. The fourth module is AI-based insect detection. A camera captures real-time images of crops. These images are then sent to the AI model for analysis. The model identifies whether harmful insects are present. If pests are detected, a signal is sent back to the robot to take action. This is one of the most important modules in our system. Once pests are detected, the robot performs targeted spraying. Instead of spraying the entire field, it sprays only on affected areas. This provides several advantages such as reduces pesticide usage, saves cost, protects healthy crops, minimizes environmental pollution. The spraying mechanism is controlled using a relay module and Arduino. Additionally, the LCD display provides real-time feedback such as detection results, environmental conditions, robot status. This makes the system efficient, precise and eco-friendly. These slides show the real-time implementation of our system. We integrated all hardware components including sensors, motors and microcontrollers. The AI model was deployed and connected with the system using Wi-Fi communication. During testing, the robot was able to move autonomously, detect obstacles, capture crop images, identify pests, perform targeted spraying. The system was tested in a controlled environment to ensure accuracy and reliability. The result shows that our system works efficiently and can be scaled for real-time agriculture use. This proves the practical feasibility of our project. These are the references used in our project. We refer to multiple IEEE and Elsevier research papers related to AI in agriculture, IoT-based monitoring, robotic spraying systems. These sources helped us understand the existing technologies and improve our system design.